Hello everyone, in this session we're going to see how biomass can be estimated with data fusion from SAR and optical sensors. The goal here is to develop random forest regression model with SAROptical data fusion in order to predict above ground biomass. For such a task, there's a need for us to choose a methodology that is backed by literature to establish the resultant model's credibility in the scientific community. The methodology for this demonstration is partially based on the approach tested by Ghosh and Behra and Ravindra, and to a lesser extent by Lee. Their works used data from SAROptical backscatter, texture, and vegetation indices to predict above ground biomass at field plot and global levels, with the backbone of regression in random forest algorithms. The considerations for SAROptical feature data selection is based on studies on SAR for estimating above ground biomass concluded that C-band backscatter leads to poor performance due to the saturation at biomass values greater than 100 megagram per hectare as established by Zhang. And also SAR has been identified to perform poorly than optical data for above biomass estimation, where the forest is of high density, while SAR texture gives encouraging results measurability in local variation in the backscatter and not the values of the backscatter. And this is also indicated by Enzart and Frank. In addition, SAR L-band penetrating power makes it not suffer from saturation until 300 megagram per hectare, making it a good choice, noted by Bezal in 2018. These are the justifications for the selection. The above scientific works have guided in giving considerations to layers from Sentinel-1 backscatter and texture, Pulsar-2 backscatter and texture, and that is from land observation, satellite 2, which is called ALOS-2, and Sentinel-2 vegetation index, and also auxiliary data, which is very important, like land use or land cover map or digital elevation model. The input data set are single images of stacked and co-registered feature bands of the proposed random forest model requirement for training needs to be generated, and platforms like Google Earth Engine can be used to assess the various bands identified from the previous discussion for the study area that will be chosen, and also for loading test size data as an asset to generate a NumPy array for the random forest model. And that is the interface of the Google Earth Engine Explorer screen. The synergic combination of sensory data from multiple sensors will provide more reliable and accurate estimates as established by the literature. Python can be used to create the random forest regression model to consume the NumPy array from the GE output. Random forest regressor is a supervised classification algorithm that is form of decision trees, as shown in the diagram. Decision trees are a type of model where decisions are made sequentially with branching results, usually used for classification or regression tasks. A random forest is simply a collection of such decision trees that are aggregated together into one final result. It functions by building a number of decision trees during training and producing the mean prediction of these trees as an output for regression. Let's look at advantages of random for why we're proposing it. It is one of the most accurate machine learning algorithms. It can handle large number of input variables, and it has reduced risk of overfitting. The performance of the proposed random forest model will depend on a lot of factors, but there are always techniques to make improvement. One of it is feature space optimization. Multi-temporal and large datasets lead to high dimensional and complex datasets due to large number of prediction variables or features, especially compared to the small reference data, can lead to high dimensional problem and leading to overfitting. To avoid this, unnecessary and unimportant features can be disregarded from the feature space that's optimizing it. The next thing is hyperparameter tuning, and that is setting the random forest function parameters to affect its learning performance. There are also other techniques we can employ, and one is ablation study, and that is by removing part of the model to judge its impact on the model's performance in order to understand the contribution of each feature to the model. Also, we can look at regional modeling, and that is by building and training the random forest on a given reference site and then using that to predict other sites within the region. This helps to investigate the ability or the capability of the regional model for predicting other sites in the region. The third one is global model, and that is training with at least one set pair from each site or giving the fraction of the total number of the reference sites from all the regions. And this also helps to establish the applicability of the global models for predicting sites in other regions. The accuracy of the model can be assessed by considering root mean square error, relative root mean square error, and also coefficient of determination, which details are provided. At the end, our model is going to look like the figure we have, where you have the reference data and site selection, then the data layer selection, then you come to our data set, and this is where you have multiple source of data: Sentinel-1 data set, Sentinel-2, and the ALOS Pulsar 2, then the pre-processing stage, which will cut across. Then from there you have the input to be generated, which we're going to use the GE to generate for the random forest model. Then you have the feature space optimization. We talked about parameter tuning, data ablation study. Then you come to the regional models, and at the end you have your predictions. So this workflow can be used to estimate biomass from optical sensing and SAR data. Here is a list of references for further studies. Thank you for your attention.